Hello dear students, welcome to our YouTube channel Wireless Tutor. Dear students, in this video we are going to discuss about the first chapter of class 10 NCERT, and the name of this chapter is real numbers. In this video we will discuss about the number sets which are present, and we will also discuss about the fundamental theorem of arithmetic as well as Euclid's division algorithm, and we will also complete the exercise 1.1. So without wasting any more time, let's get started. So dear friends, let us know, in the universe, all of the numbers are categorized into two parts. So there are basically two types of numbers: real numbers and imaginary numbers. Imaginary numbers. These imaginary numbers are also called as complex numbers. Complex. So real number set is also again divided into two parts: rational and irrational. In the rational number set, there are also subsets like integers. Then in the integer set, there is whole number sets exist, whole numbers. Then in the whole number set, natural numbers exist. So in this way, we can say that numbers are divided into two parts. Numbers are divided into two parts: real and imaginary. Again, real numbers are again divided into rational and irrational. And rational number sets contain integers, whole numbers, and natural numbers. So if you talk about the natural numbers, then what are the natural numbers? The numbers which are used for counting purpose. For example, suppose you want to count the number of students or number of things or objects, then you will definitely count from 1, then move on to 2, then 3, and up to infinity. So these numbers are especially used for counting purpose, and those numbers which are used for counting purpose are called as natural numbers. So this natural number set is denoted by capital N. So in the natural number set, the 1 is the smallest natural number, smallest, and there is no greatest natural number, because suppose you think that x is the natural number, and if you add 1 with that number, then you will get the next number. So in this way, this number set moves towards infinity. That means there are infinite numbers in the natural number set. Then move on to the whole number sets. Whole number sets are expressed by capital W, or sometimes this is also called n star. What is this whole number set? All the natural numbers along with 0. If you include 0 along with the natural numbers, then you will get the whole numbers. This is the natural number set, and if you include 0 in this set, then you will get whole number set. So the smallest whole number is 0. So what are the integers? Integers are integer is a set of all of the natural numbers, their negatives along with 0. What I told you, all the natural numbers, their negatives along with 0 are called as integers. So integer set is denoted by Z, capital Z. It starts from 0 and moves as plus or minus 1, then plus or minus 2, and so on. You can also write this integer set as just put 0 at the middle, then write on the positive integers. Those are 1, 2, 3, and so on towards right, and write down the negative numbers minus 1, minus 2, minus 3, and so on towards left. Next, move on to the rational numbers. What are the rational numbers? Rational numbers, the numbers which can be represented in the form P by Q. If a number can be represented in the form P by Q, there is a condition that P and Q must belongs to Z, and Q cannot be 0. So this is the essential condition for every number to be rational. Let us take for example 2 by 3. 2 by 3 is a rational number because it is expressed in the form P by Q. Here 2 is P and 3 is Q, and both belongs to the set Z. That means both are integers, and in this case we can see that 3 is the denominator, and which is not 0. So 2 by 3 is a rational number. Remember, rational numbers rational numbers cannot be represented in the roster form or tabular form. We cannot represent rational numbers. We have represented natural numbers in the roster form. Roster means list form. We also represented whole numbers in the roster form. Again, we also represented integers in the roster form. But we cannot represent rational numbers in the roster form. We can only represent rational numbers in the set builder method. How can we write that? Rational number sets are represented as capital Q. Q belongs to X such that X is P by Q. That means X must be in the P by Q form, where P comma Q belongs to Z. That means both are integers, and Q is not equal to 0. This is the set builder form of every rational numbers. So irrational numbers, that is the contrary of rational numbers, those numbers which cannot be represented in the form P by Q, then those are called as irrational numbers. So the example of irrational numbers, are root 2. We cannot represent root 2 as in the form P by Q. If you think that we can write root 2 as root 2 by 1, this is also P by Q form. But there is a condition that P and Q must belongs to Z. That means these P and Q must be integers. But here root 2 is not an integer. That's why this is not the correct expression in the form P by Q. So root 2 cannot be a rational number. So imaginary or complex numbers are not real numbers because we express by using a symbol that is I. 5i. I means root over of minus 1. When there is a negative number under root, then the total number system changes into the imaginary or complex numbers, because these numbers doesn't actually exist. This is the brief information about number sets. Now move to the next slide. Let us know what is Euclid's division algorithm. What does it says that? Euclid's division algorithm says that any positive number can be divided by any other positive integer b in such a way that it leaves remainder a. Suppose a is a number. If you divide this number by b, then you will get some quotient, that is q, and you will also get some number, that is remainder, that is denoted by r. So basically this is the division algorithm. Let us take an example. Suppose you took a as 17 and b as 5. After dividing 17 by 5, we'll get 3 as quotient, and just subtract 15 from 17, you will get 2 as the remainder. In this case, here q is equal to 3 and r is equal to 2. And we can express this as Euclid's division algorithm, that we can write 17 is equal to, that is b into q. That means here b is equal to 5 into 3 plus 2. So this is what says Euclid's division algorithm. That means any number, if any positive number a that is divided by any other positive number b, then we can write this expression as a is equal to bq plus r. This is the Euclid's division algorithm. Let us take another example. Suppose I took a is equal to 36 and b is equal to 7. Then I can write 36 is equal to 7 into 5 plus 1. Here there is a condition that r must be less than b, because if you think that you will write 36 as 7 into 4, 7 into 4, that is 28 plus 8, but there is a condition that this remainder should not be greater than the divisor. That means this must be less than b. So in this case we can write 7 into 4 plus, this is 7 plus 1. By taking common 7 from this, then you will get 7, 4 plus 1 plus 1. Then that is 7 into 5 plus 1, which was earlier expressed. Look at this, that 36 is equal to 7 into 5 plus 1. So this expression was converted into this form. So this is nothing but, this is the another type that is written. So this is true apart from or except from the order. So you wrote this in a particular order, and this is another order. So Euclid's division algorithm says that if you divide a with b, then you will get a quotient q and remainder r, where r is less than b. So that can be represented as a is equal to bq plus r. This is over. I think you have completely understood this Euclid's division algorithm. Let us move to the next slide. So let us know what is fundamental theorem of arithmetic. So it says that any composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factor occurs. We will understand this with examples. Suppose you took any composite number, that is 18. So we can find the prime factors of 18. We can divide 18 by 2. Then we will write 9 here. Then 9 can be written as 3 into 3. So 18 can be represented as 2 into 3 into 3. So this can be also written as in the exponential form, that is 2 to the power 1 into 3 to the power 2. So this is what the fundamental theorem of arithmetic says that so here 18 is a composite number and 18 is represented in the form of the product of prime numbers, because 2 is a prime number and 3 is also another prime number. So every composite number can be represented in the in the product of primes. So here is A is a composite number and A can be represented as the product of primes, that is the P1, P2 and Pn, these are the prime numbers, and A is represented as the product of these prime numbers. So let us take another example, that is 48. Just take the prime factors of 48 to 24. Here 2, 12, 2, 6, 2, 3. So 48 can be represented as 2 into 2 into 2 into 2 into 3, or 2, this can be represented as 2 into 4 into 3. So the first part is clear that every composite number can be represented as the product of primes. This is clear. But the look at this second statement. This factorization is unique apart from the order. Then what do you mean by order? Suppose you wrote 48 as 48 is equal to 3 into 2 to the power 4. In the first line, you have wrote that as 2 to the power 4 into 3, but in the second line, it is written that 3 into 2 to the power 4. So the order is changed, but this is not totally different from each other. These are equal because we can write 3 into 5 as 5 into 3. So this is the change of order only. So it says that apart from order, this factorization is unique because you cannot write 48 as 3 into 7 into 2 or any other, because this factorization is unique. That means the factorization should involve the prime factors of 48. So this is fundamental theorem of arithmetic. I think all all are clear. Next, formation of the factor tree. Then how can we plot a factor tree? Suppose you are asked to write down the factor tree of 72. Then how to write the factor tree? Uh, First try to divide the composite number with the smallest prime factor. So the smallest prime factor is 2. If this number is not divisible by 2, then take 3. If that is not also divided by 3, then take 5, and so on. So it is convenient to start with the smallest prime number, that is 2. So after dividing 72 by 2, then we will get 36. Again divide this by 2 because it is divisible by 2. Then we will write 18 here because 2 into 18 is equal to 36. Again divide 18 with 2, then we will write 9 here. Then again divide 9, because 9 is not divisible by 2, we have to try with a 3. If that is not also divisible by 3, then we will choose other prime numbers. But it is clear that 9 is divisible by 3, so just write down as 3 into 3. So if you notice the entire spectrum in a reverse order, then you will see that there is a tree formed. So this is a tree shaped. These are the branches. Again, these are the branches. So this is just like a tree form. So this is the prime factor, prime factor or factor tree of 72. So you can also form the factor tree of 56. I will perform this for you, and I will give some other homework questions. You will try this. Just write down 2 here, and after dividing 56 by 2, we will get 28. Then again write 2 here and 14 here. Again divide this with 2 and write down 7 here. Since 7 is a prime number, then don't perform this activity further. So this is the factor tree of 56. Let us move to the next slide. Check whether 4 to the power n ends with digit 0. So suppose a number that is 50 or that is 60. For any number to end with digit 0, there must be two factors, 2 and 5. So we need to check whether in the prime factorization of 4 to the power n, both these factors present or not. If both these two factors are present, then we can write that this number 4 to the power n ends with digit 0. Otherwise, it cannot end with digit 0. So solution. So how to write? Let us perform. Let us take 4 to the power n, any composite composite number as a. So according to the fundamental theorem of arithmetic, every composite number that can be represented as the product of primes. So we can write a is equal to 4 to the power n. Since 4 is a composite number, we can write this as the 2 to the power 2 and whole to the power n. When both these powers are, or when there is a power over power, suppose there is a to the power b whole to the power c, then we can write this as a to the power bc, the product of these two powers. So in this case also we can write 2 to the power 2n. So here you can see that this 2 to the power 2n, there is only 2 exist as a prime number. There is no other prime number exist other than 2. But every number which ends with digit 0 must possess 2 and 5 as its prime number. So in the prime factorization, in the prime factorization, factorization, prime factorization of 4 to the power n, 5 does not exist. 5 does not exist as a prime factor. Prime factor. So, or thus, it is clear that 4 to the power n cannot end with digit 0. Digit 0. I hope this is clear. I have a task for you. You have to write down. You have to write down whether 6 to the power n can end with digit 0 or not. You have to write yourself. Next, its application of fundamental theorem of arithmetic, finding LCM and HCF in the prime factorization method. We can write down, or we can find out the LCM as well as the HCF in the prime factorization method. So through example we will understand this process. Here the example is, find the HCF and LCM of 96 and 108. So just write down or just find out the prime factors of 96. Then taking 2, that is 48, to 24, to 12, to 6, to 3. Then we can write the prime factorization, prime factorization of 96. 96 is equal to 2 into 2 into 2 into 2 into 2 into 3. So we can write this as 2 to the power 5 into 3. So again, prime factorization of 108, then 254, then 227, 3, 9, 3, 3. So prime factorization, prime factorization of 108. So we can write 108, 3, 108 is equal to 2 into 2 into 3 into 3 into 3. So this is 2 to the power 2 into 3 to the power 3. Then move to the definition. What is SCF? What is SCF? The product of the smallest power of each common factor in the numbers. That means the factors must belong to both of these prime factorizations. Suppose 2 exist here and 3 exist here. So, but in this case, if 3 doesn't exist, then 3 is not a common factor. So we need to first ensure that the factors must be present in the prime factorization of both these numbers. So FCF, what will be the FCF? So FCF is the product of the smallest power of each common prime factors. That means what are the common prime factors? 2 is a common prime factor and 3 is also common prime factor. But it is written that it is the smallest power. In this case, it is written that 2 to the power 5. That means the power of 2 is 5. Here, power of 2 is 2. So, what is the smallest power? 2. Then we will write in SCF as 2 into 2. Similarly, here 3 into 3 to the power 1. Here 3 to the power 3. We will take 3 to the power 1. That will be 2 to the power 2 is equal to 4 into 3. 4 multiplied by 3 is equal to 12. So the FCF of, of 96 and 108 is 12. Then how to find out the LCM? So look at the definition. LCM. It is the product of the greatest power of each prime factor. Each, not the common. Here common prime factor. Remember, in HCF you have to write the common prime factors. But in LCM you have to write all of the prime factors. So what are the prime factors? 2 and 3. Just write down the highest power of each prime factors. Then the highest power of 2 is 5 and the highest power of 3 is 3. Then we can write this is 32 into 27. Then this will be 27 to the 54, 4, then K 5, 27 3 the 81. After adding 81 with 5, we will get 86. So the LCM of 96 and 108 is 864. Next, just write down. There is a task for you. You need to write down the LCM of 56 and 72. Next, then write down here. There are three numbers. We need to find out the LCM and LCM of three numbers. Similarly, there is nothing different. Just write down 56 here and find out its prime factors 2, 28, 2 14, 2 7. So 56 can be written as 56 is equal to 2 into 2 into 2 into 7. This can be written as 2 to the power 3 into 7. Similarly, find out the prime factors of 72, 2, 36, 2, 18, 2, 9, 3, 3. So 72 can be written as 2 into 2 into 2 into 3 into 3. That is 2 to the power 3 into 3 to the power 2. Similarly, find out the prime factors of 36, 2, 18, 2, 2, 9, 3, 3. So 36 is equal to 2 to the power 2 into 2 into 3 into 3. So this can be written as 2 to the power 2 into 3 to the power 2. So according to the definition, what is SCF? So SCF of 56, 72, and 36 is equal to, according to the definition, we need to write all the common factors. 2 exist here and 2 also exist in all of these three prime factorizations. So we need to write 2 as a common prime factor. 7 is not a common prime factor because 7 is not present in the prime factorization of 72 and 36. So we don't need to write 7. Similarly, in the case of 3, 3 is not also a common prime factor, though the 3 exists in the prime factorization of 72 and 36, but 3 doesn't exist in the prime factorization of 56. So there is only one common prime factor, that is 2. According to the definition, it says that we need to write the smallest power of this common prime factor. Here 3, here 3, here 2. So we need to write 2 as the power. So it is 4. Then the HCF of 56, 72, and 36 is 4. Similarly, LCM of 56, 72, and 36 is equal to, it says that we need to write all of the prime factors, not the common prime factors only. 2 is a prime factor, 3 is also a prime factor, and 7 also a prime factor. And according to the definition, it says that we need to write the highest power of the prime factors. So 3 is the highest power of the prime number 2, and 2 is the highest power of 3, and 1 is the highest power of 7. So we need to write as 8 into 9 into 7. This is 9 8 is 72 into 7. Then the answer is 7 2 is 14, 4, remaining 1, 7 7 is 49, 50. Then the LCM of these three numbers is 504. So there is a task for you. You need to find LCM and SCF of 28, 32, and 40. Next, then exercise 1.1. Express each number as a product of its prime factors. We have already done here, but I will find the solutions here. The first one, 140. Prime factors, write 2 here, and this will be 70. Write 2, 35, then 5, 7. Then what are the prime factors? Prime factors 2, 2, 5, and 7. So we can write the prime factors. The prime factors of 140 are 2, 5, and 7. Next, um, you can find the other prime factors of these numbers yourself. Move to the next question. Find the LCM and HCF of the following pairs of integers and verify that LCM and HCF is the product of the two numbers. So you can find yourself. I will find the first one for you. 26 can be written as 2 into 13. Similarly, 91 can be written as 7 into 13. So what is SCF? SCF is the product of the smallest power of all the common factors. Here, which is the common factor? You can see that 13 is the common factor here. So 13 has the smallest power 1, so SCF is 1. Then what is the LCM? LCM is equal to the product of all the common factors. So all the prime factors, 2 into 7 into 13. 2 sevens are 14 into 13. This is uh, 10. This is probably 182. 182 is the right answer. Then we can verify. Uh, take the left side, that is LCM into HCF is equal to 182 into 13. 13 to the 26, 6 remaining 2. 13 it's the that is 104, 104, 106, 6, 10. 13 ones are 13 and then 10. Sorry, that is 23. So this is the value of the product of LCM and HCF. We need to find the product of these two numbers. Then the product of these two numbers, product x comma y is equal to, that is 91 and 26 is equal to, if you multiply this, and then you will get 2363. So thus, or therefore, LCM into HCF is equal to product of the numbers. Product of numbers. This is verified. Now move to the next slide. Question number 3. Find the LCM and HCF of the following integers by applying the prime factorization method. I have already told you, you can find yourself the LCM and HCF in the prime factorization method. Then move to the next question. Given that the HCF of 306 and 657 is equal to 9, find the LCM. So how to find the LCM? We have the formula LCM into HCF is equal to product of the numbers. Product of the numbers. So we need to find out the LCM. Just put down the values which are given. Here HCF is 9, so LCM into 9. Since HCF is 9, so write down 9 here. Product of these numbers, that is 306 into 657. Then find the LCM. LCM is equal to 306 into 657 divided by 9. After dividing, you will find, uh, I prefer to use calculator here to save your times. 657 divided by 9. Then the answer is 22,338. This is the answer. Next, check whether 6 to the power n can end with digit 0. I have already told you that. Let's try it. Solution. 6 to the power n can be written as 2 into 3 to the power n. This can again be written as 2 to the power n into 3 to the power n. So in this case, you can see that in order to end with digit 0, there must be Then in order to end with and to end with digit zero a number to end with digit zero a number must contain must contain 2 and 5 as its prime factors. 5 is absent in the prime factorization of 6 to the power n. Therefore 6 to the power n cannot end with digit zero. Next, explain why 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. So let us check the first 7 into 11 into 13 plus 13. This is a term and this is another term. There are two terms in this expression. So just take 13 common out of this expression. After taking 13 common, you will get 7 into 11. 7 into 11 plus here 1. Then we can write 13 to 77 plus 1. 13, 13 into 78. And 78 can be written as 13 into 2 into 39. So here, this expression you can write that this number is expressed as product of primes. Product of primes. Primes. That's why this expression 7 into 11 into 13 plus 13, this is a composite number. Then check for the other. 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. You can see that there are also two expressions taking common 5 from these expressions. Then you will get that 5 follows 7 into 6 into 4 into 3 into 2 plus 1. So after writing this entire expression, the entire expression will be converted into this will be again converted into the product of primes. Product of primes. Check yourself. Product of primes. That's why this is also a composite number. Next question. 7. There is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field, while Robbie takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting point? Then basically we need to find the LCM, sorry, LCM of LCM of 18 and 12. After finding this LCM, then you will be able to find out after how many minutes they will meet again. Solution. Finding the LCM of 18 and 12. 18 can be written as 2 into 3 into 3. That is 2 into 3 to the 2. Similarly, 12 can be written as 2 into 2 into 3. That is 2 to the power 2 into 3. So sorry, we need to find LCM. LCM of 12 and 18 is equal to 2 to the power 2 into 3 to the power 2. That is 4 into 9 is equal to 36. So after 36 minutes, they will meet again. So this is all about for today.